In this video, I'm going to talk to you about applications of Newton's second law. And Newton's second law simply says that the net force is equal to the mass times the acceleration. It certainly seems simple enough. Again, if we're looking at problems that are two-dimensional, and we will be, this looks more like the net force horizontally is mass times the acceleration horizontally, and the net force vertically is the mass times the acceleration vertically. A lot of times we'll have something that's accelerating up or down, but not horizontally. Or we might have a situation where something is accelerating horizontally, but not vertically. Let's do an example from the book. This example is called a simple accelerometer. And you could actually do this. You would need a protractor. Protractor is one of those things we use to measure angles. And then you'd have to tie something to the protractor, like a key or another small mass. Normally it would hang straight down. Anytime you were moving at a constant speed, the mass would be at a constant speed, it would hang straight down. But if you were to accelerate, what you'd see is that it would come back here somewhere. We're going to assume that that's a constant acceleration. So if you have a constant acceleration, it's not going to change. It's going to stay at the same angle, whatever that angle measurement is. We're going to call this angle from here to here beta. And it's the angle that the strain makes with the vertical. How many degrees has it moved from when it was hanging straight down? And we want to be able to use that angle to determine the acceleration. Now, off the top of your head, you're probably going, I wouldn't have any idea how to use that angle to determine the acceleration. But the key to any problem that involves forces is a good free body diagram. So I'm going to draw a free body diagram and see what we can figure out. We want to look at what's happening to the mass. Well, the mass's free body diagram looks like this. We know that weight goes straight down. Even though, obviously, the string is not hanging straight down, the pull of gravity is always straight down towards the center of the earth. We also have this string that's attached, which is providing some tension. So the tension goes off at an angle like this. If you think about it, you probably don't have to think very long. If you were to extend this out the other way, you can see that those would be vertical. But this angle that it makes right here, we want to continue the y-axis. That angle to beta, that's the angle. Here's our x-axis. Obviously, what we're going to have to do is take the tension and break it into components because we've got tension that doesn't lie on either one of the axes. Now, unfortunately, they did not measure. We are not measuring our angle from our positive x-axis, so we're going to have to rely on a little bit more trig knowledge. But we can see, even before we apply that little bit more of trig knowledge, that when we do our free body diagram with components, it's going to look more like this. The weight, or mg, is going to be pointing straight down, And then the tension's going to have two components. It's going to have a component this way. We'll call that Tx. And it's going to have a component this way. We're going to call that Ty. Now, we know the acceleration is to the right. This is like glued to your car window. You put it right there by the driver's side. Don't do that. Put it by the passenger side and window and let your passenger tell you what angle it measures when you accelerate. And we can see really quickly that Ty is just going to be equal to the weight, mg. The other thing we can see then is that the acceleration is related to Tx. Okay, so we need to figure out how do we get Tx and Ty if we know this angle. Well, we can do some of that trig that we do when we get desperate. We can say, look, this is going to look like this. Trying to decide which way I want to draw. Tx, Ty, and of course, the hypotenuse is just T. If this angle is beta, then this angle is beta. And we're going to have to go back and use our trig again. Cosine beta, cosine is always adjacent over hypotenuse. Well, the adjacent is Ty, and the hypotenuse is T. So we end up getting a situation, that's supposed to be an H for hypotenuse. So when we solve for Ty, we realize that Ty is T cosine beta. Again, it's like that inclined plane. If we're not measuring the angle from the positive x-axis, we can't say the x component is going to be cosine. In this case, the y component comes out to be cosine, and again, it's because we're measuring from the y-axis, not the x-axis. If we do sine beta is opposite over hypotenuse, and that comes out to be Tx over T. So when I solve for Tx, I get that Tx is T sine beta. Okay. I'm running out of boards. I'm going to write down what I think is important up here. Tx is T sine beta. Ty is T cosine beta. We're asked to try to solve this where we get the acceleration in terms of the angle, where the only thing we don't know is the angle. So we're going to have to figure out this tension here. I know, looking at my free body diagram, when I look at the vertical equation tells me that Ty has to equal mg. So now I have mg equals T cosine beta. I know that Tx has to equal mass times acceleration in the x direction. Notice I only have one horizontal force. That one horizontal force is that horizontal component of this tension. Those are the only two forces, the weight pulling down and the tension. So Tx has to be telling me mass times horizontal acceleration. So I have mass times acceleration equals T sine theta. All right, two equations, but I just really need to get rid of this t. What I'm going to do, if I solve for t, I realize that t equals mg over cosine beta. I want to make sure everybody understands what I did here. I just solved this right here for t. If I solve that, that gives me t equals mg over cosine beta. So I do have an expression for the tension that depends on the angle. Let's finish solving this. Notice right away we've got sine beta over cosine beta. That's tangent beta. So I'm getting MAX equals mg tangent beta. But the m's will cancel out. I have an m on both sides. So I end up getting that my acceleration is just g times tangent beta. That's a pretty simple equation. If you know the angle and you know the acceleration due to gravity, you can find the acceleration of the car. Let's think about this for just a little bit. At 45 degrees, tangent is 1. So at 45 degrees, it means your horizontal acceleration is exactly equal to g. That really makes sense if we think about it. If you're this mass, if your acceleration is 9.80 this way and acceleration due to gravity is 9.80 this way, you would expect the angle to be 45 degrees. It makes perfect sense that the angle is 45 degrees. Notice I cannot get it to go all the way to 90 degrees. In order to go to 90 degrees, I'd have to have the acceleration reach infinity. So it will never go where it's straight out here at 90 degrees. Okay? Tangent of 0 degrees, let's see, would be 0. And that makes perfect sense too. If the angle's 0, it's hanging straight down, then we know it's not accelerating horizontally. Go back through this, look at the example in the book and spend some time on it. But it's an interesting problem. And really, once you draw the free body diagram, you realize this is always going to equal the mass times the acceleration. These two are going to cancel out, of course. Let's look at a different example. Erase all of this. This is about a glider on an air track. The purpose of the air track is that it minimizes friction. So for our purposes, this is frictionless. Here's our air track. Air tracks usually look like a little triangular shaped prism. They're V-shaped with air coming out. And riding along on the top of that, we have a glider. And the glider almost floats on top of that air. It usually looks something like this. And that glider is attached by a string and a pulley to a mass. So here's the pulley. Here's a string, nice and parallel. And then here's some mass. We're going to call this mass 2. We're going to call this mass 1. We've got 2 different masses. The pulley is frictionless and ideal. So if we have a frictionless ideal pulley, there's a couple of really important ideas. If we have a frictionless ideal pulley, the tension in this string and the tension in this string are the same. So we usually just call that T. T1 and T2 are exactly the same. We're going to call that T. Another thing we have to think about anytime you solve is your frame of reference. For our purposes, we're going to let positive be to the right. Well, that's not unusual. But what that means, since this is a system, these two masses are connected, it means that I also have to let down be positive. Because these two masses actually move together. So M1 and M2 move together. That means that they will have the same acceleration. That's an important idea. T1 and T2, they have the same tension, and they move together with the same acceleration. I really don't need the 1 and 2 now that I know that those are the same. I do need 2 separate free body diagrams. Anytime I'm drawing something and I have 2 masses, each mass has to have its own free body diagram. So for mass 1, if we were to draw its free body diagrams, it would look like this. Its weight would be down. There'd be a normal force up. And the tension in the strain would be to the right. If we had friction, friction would be to the left, but we don't have any friction. They told us we're treating this as if this was a frictionless system. Friction's going to be in the next video. So there's the free body diagram for mass 1. For mass 2, here's mass 2. It too has its weight going down. That's mass 2 times G. And it has tension going up. All right, we can write an equation for both of these. Remember, the net force equals the mass times the acceleration. So if I want to do it for M1, these two will be equal. The weight pressing down against the air track is going to be equal to the normal force pushing up. So for mass 1, the equation is just T equals M1A. Now, for mass 2, it actually has 2 forces. We don't know that these are equal. They're probably not. If these two are equal, there's no acceleration. But we've kind of been led to think this is an accelerating system. I think it is. In that case, we just need to remember that down is the positive direction and up is the negative direction. So the net force here will be M2G minus T, and that equals M2 times the acceleration. This is the net force, the downward force minus the upward force. This is the positive one because we said if we're going to treat going to the right as positive, we have to treat going down as positive. So I have 2 equations. I have 2 unknowns. Theoretically, I assume that I can find out M1 and M2. I know what G is. But what I don't know is the relationship between tension and acceleration. If I add these two equations together, I get M2G equals M1A plus M2A, or M2G equals M1 plus M2 times A. Let's stop and think about this in terms of the whole picture, because I think this is going to make a lot of sense. The net force, the downward pulling force, is this M2G. That's the force that's pulling the system down. That's our net force. But the mass that it's pulling is not just M2, it's pulling M1 and M2. So we have this much larger mass here. Net force equals mass times acceleration. If I solve for A, I get M2G over M1 plus M2. We can do this problem with known masses, but they didn't give me known masses, they just gave me variables. Let's think about it. It makes sense that if we let mass 1 get very, very large, if this turns into a really big mass, that the acceleration would get really, really small. On the other hand, if we leave mass 1 alone and we let mass 2 get very, very large, we can see that we'll gradually be approaching free fall. If we let this get bigger and bigger and bigger, this will have less and less of an effect, and M2 over M1 plus M2 would eventually approach 1, in which case the acceleration would look like free fall. This makes sense. It's always good to stop and think about extremes. Okay? What happens if M2 is really, really tiny? Then we get very, very little acceleration. We just get G over M1. Okay. Oh, we didn't answer the question about the tension in the rope. Well, the tension in the rope is really easy, because the tension in the rope is just mass 1 times the acceleration. So if I want the tension, I'm going to borrow a little space here, is simply mass 1, mass 2 times G over mass 1 plus mass 2. All I did was take this answer, multiply it by M1, and that gave me an equation for the tension in the strain. Okay, I'm going to do one more example. And on the one hand, it's a harder example, but on the other hand, we're going to put numbers in the problem, and putting numbers in the problem may make it seem much easier. This problem comes out of the textbook, chapter 5, problem number 24. And we're given a picture. We have a ramp that's at a 30-degree angle. At the end of this ramp, we have a pulley. On the ramp, we have a box that's 50 kilograms. Call that box number 1. It's connected by a pulley to box number 2. And box number 2 weighs 30 kilograms. This is an ideal frictionless plane, and this is an ideal frictionless pulley. If I have an ideal frictionless plane and an ideal frictionless pulley, I know a couple of things. Like, I know the tension in the rope here and the tension in the rope here will be exactly the same. I know the whole system will accelerate together if it accelerates. I don't know yet whether it actually will go down the ramp or go up the ramp, which way that larger box is going to move. But I'm going to continue to let this be the positive direction, which means this is the positive direction. I know I need 2 free body diagrams. It's really obvious to me. If we look at box 1, its free body diagram looks like this. Its weight comes straight down. It always does. The tension is going up the ramp at a 30-degree angle. If you wanted to draw that angle in, you could. That's 30 degrees. And then the normal force is perpendicular to the ramp. Those two will be at right angles. Right away, we can see with box 1, we have to do what we do on inclined planes. We have to take that weight, and we're going to need to break it into some components. But even before we do that, let's see what it weighs. We know that the weight will be 50 times 9.80, which is 490. So this first block is 490 newtons. But what I want to do is take that and see, well, how much of that is going to be Wy, and how much of that's going to be Wx. In other words, I want to replace that weight by its components. Wx is W sine alpha. The good news is we know the rules for weight on an inclined plane now, so I don't have to redo it. For an inclined plane, the horizontal component, W sine alpha, so that's going to be 490 sine 30. And when I do 490 sine 30, I get 245 newtons. So I know which direction this is, but I don't know how big it is. That's going to be helpful in a minute. When I do Wy, that's W cosine alpha. That's 490 cosine 30. And that comes out to be 424 newtons. Okay? Well, I know a lot of stuff now, and if I want to erase the original free body diagram with the 490 going down, I kind of have something that looks like this now. I'll clean it up. I know that this is 424. Most of the weight is still pressing against, and I know that this is 245. Okay, so I have some good stuff. I'm going to come back and write an equation in just a minute, but let's go ahead and do another free body diagram. We really got to get good at these and good at understanding them. So for box 2, there's box 1. It's really simple. It's got its weight coming down, which is going to be 30 kilograms times 9.80. That's its weight. And it's got the tension and the strain going up. Okay, so 30 times 9.80, put that in a calculator, it comes out to be 294 newtons. Now, avoid the temptation to say, oh, the tension is 294 newtons. Not if this thing is accelerating. If this is accelerating, these two forces can't be equal. We think it's accelerating. So we need to be really careful. But we can start getting equations. We can write the equation for F net equals mass times acceleration. If we do it for box 2, when we do the net force, we need to remember that down is positive and up is negative. So we get 294 minus T equals 30A. That's the equation for box 2. We had a pretty simple free body diagram. 294 newtons in the positive direction and the tension going up in the negative direction. That gives me the net force. It's the difference between those two. It equals 30A. So that's for box 2. When we look at box 1, it is reasonable to say these two are equal because we know the box is not accelerating perpendicular to the plane. However, these two are the important ones. In this case, this equation looks like T minus 245 equals the mass times the acceleration. And this box 1 had a mass of 50. Okay, this is really easy to solve because it's just a simple system of equations. We know the acceleration is the same for both of them. We know the tension is the same for both of them. Notice this has a negative T, this has a positive T. So if I add these up, the T's are going to cancel. I'm going to get 294 minus 245, which is going to be 49, equal 80A. And when I do 49 divided by 80, I get A is equal to 0.6125 meters per second squared. Now that's too many significant digits. The problem had 3. So we're going to write 3 for our answer. That answered the question. They actually did not ask us to find the tension in the rope. But I want to talk about the tension in the rope for a minute. If it's accelerating, if this box is moving up the ramp, and it is, this is a positive acceleration, so we know the box is moving up the ramp, then I think the tension has got to be greater than 245 newtons. If this box is going to accelerate, the tension has to be more than 245. However, let's go over here and think about box 2. Box 2 is accelerating downward. Well, the downward force here is 294. So in order for this to accelerate downward, this tension better be less than 294. So I think the tension has to be more than 245. I think the tension has to be less than 294. If I want to solve for tension, I just solve one of these equations like this. This will give me tension equals 245 plus 50A. So if I plug in my number before I round it, the tension comes out to be 276 newtons. And that makes perfect sense. 276 is more than WX. It's more than 245. It's enough to pull this up the ramp. And 276 is less than W2. It's less than 294, so it makes sense that that would go down. So that's the solution to number 24 in chapter 5. Okay, so that gives you some ideas about how we can apply Newton's second law.